All right, welcome to lecture 10. What we're going to do today is we will discuss how to do real calculations with a grand canonical distribution. And I'm going to show you why the grand canonical distribution is a good thing. So this will be a moment of epiphany for you. And hopefully it'll make it all seem a lot clearer. So let's remind ourselves where we were last time. Last time we were dealing with to solve the problem of a system of non-interacting ideal fermions. So as usual, we're looking at the system where we have over here on the right-hand side a box with particles bouncing around in it. It's an isolated box. We have agreed to look inside the area shaded in green, which I've called S, the system that we are interested in. We've drawn a little border around that and said that's the system that we're interested in. The particles are flying in and out of that system, carrying with them particle number and energy as they do so. And so in that part of the system, in that part of the isolated box, the system has got fluctuating particle number and fluctuating energy, and it is in equilibrium, therefore, with a reservoir, which is the rest of the system. And that's how we think about the grand canonical distribution as being a very natural way to think about interacting or non-interacting particle systems. The problem that we're trying to look at is a system of non-interacting fermions. And so that means that the many-body wave function of the system will, in some sense, be a product of wave functions for the individual single particles, but they have to be anti-symmetrized in a certain way in order to take account of the quantum statistics of fermions as opposed to bosons. So we're not going to just get into the specifics of how one does that. You've probably learned about that in quantum mechanics. It's not important for what we're doing here. So the single particle, so we'll call those the single particle quantum states to differentiate between the many body quantum states that we will be dealing with when we look at interacting systems. And those single particle quantum states can be occupied by either 0 or 1 particle because we're dealing with fermions. The particles are under collisions where, as usual, when we talk about an ideal system, we actually are thinking that there is some very weak interaction that we've turned on so that the particles actually have mechanisms for having transitions between states, and eventually they will attain equilibrium. Under those collisions, they transition between different single particle quantum states, so the energy of the state changes and the occupation number changes. And so we can think then of single particle quantum states as being an abstract system that is in thermal and diffusive equilibrium with other single particle quantum states. They're in thermal equilibrium because they exchange energy. They're in diffusive equilibrium because particles transition between the single particle quantum states. So when we derived the grand canonical distribution, I did it for any arbitrary system. It was just a system which is an abstract thing, so it can be anything that I like, and we have chosen as a trick, that's what we did at the end of last time, to apply it to the single particle quantum states themselves as considered to be a system. So a system could be a bunch of particles in a box. It could be a single particle quantum state with occupation numbers and energy associated with it. So there can be any sorts of labels that you like. So then we wrote down the single particle quantum state grand partition function, and that I've drawn over here. So there it is, chi sub I, and all we have to do is sum over the occupation numbers of the Gibbs distribution. The Gibbs distribution has two parameters, the beta, the 1 over kT, and mu, the chemical potential. The energy of the single particle quantum states is epsilon I, and so we have that the Boltzmann factor looks like I've shown you there. The temperature and mu are the same for all the single particle quantum states because they're all in thermal equilibrium. And so there's only two terms in that sum, so we can write it out as 1 plus the exponential. And then if I want to work out then the average occupation number of the state, then what I do is over here on the left-hand side is I write down the occupation number Ni times the Boltzmann factor, the probability of being in that state, divided by the grand partition function for that single particle quantum state, and I get the answer shown over at the bottom, which is the Fermi-Dirac distribution. Okay, so if you followed that, as I hope you all have, then the next question you would want to know the answer to is, okay, but that's fine, but how do I determine mu? Where does mu come from? And this actually is the biggest sort of uncertainty that I've seen with students in dealing with the grand canonical distribution. And the answer is there is always a constraint that determines mu, just like there's a constraint that determines the temperature. The constraint that determines the temperature is that the average energy is something that is specified. With the chemical potential, the constraint is that the number of particles, the expected number of particles is equal to n. So there's always a constraint equation, and that's the term that I will use. And that constraint equation says, if I know the average occupation number of any single particle quantum state, Fi, then if I add up the occupation for all the particles, for all the single particle quantum states, I have to get the total number of particles in the system. And so that's what n is. So, but when we're in the grand canonical distribution, n is not a constant, it's something that is fluctuating. So when I write down n, what I'm really thinking of is the expected value of n. So that's the constraint equation. And you can see why this is the right answer, because if you look at the form of Fi, so let me just write that down again, just for convenience. So this Fi is 1 over 1 plus e to the beta epsilon I minus mu. So that's what it is. So that's sum over states. Sum over I is a sum over states. Epsilon I is the energy levels of those states. So this is something that is known by solving the quantum mechanics problem. So this is known from quantum mechanics. So if you're dealing with, say, isolated particles in the box, you know what the energy levels already are. So that's given by doing the quantum mechanics. So whenever you're doing statistical mechanics, remember, whether it's classical or quantum statistical mechanics, the first thing you do is solve the quantum mechanics problem or the classical mechanics problem, and then you put in the statistics afterwards. So in this case, we solve the quantum mechanics problem to know what the energy levels are, the single particle quantum state energy levels, know what those quantum numbers are. That tells us what Fi is. Beta is 1 over kT, so we know what that is. So if I know what the average occupation number is, if I plug this Fi into my constraint equation, if I choose mu to be any arbitrary number, I can calculate the left-hand side, and it won't give me the number that is on the right-hand side. So I have to then choose mu in such a way that if I plug this form, the Fermi-Dirac distribution, into the constraint equation, it will give me the right number on the right-hand side. So the point about the constraint equation is that this equation determines mu. This constraint equation determines mu. And why does it? If we had the wrong value of mu, then the sum, or in fact, summing over states in returning to be an integral, the sum over integral over states will not give the number that should be on the right-hand side. let's suppose that you know that the number of particles in the system, the mean number, is 6 times 10 to the 23 particles. So now, if I do the sum on the left-hand side, that's a sum or an integral over states. I know what beta is, that's just the temperature. I know what epsilon I is, that's just the energy levels. So as I vary mu, that's the sum on the left-hand side or the integral on the left-hand side will change its value. And so the value on the left-hand side has got to be equal to the value on the right-hand side. So just putting in an arbitrary value of mu in there won't work. So you have to choose a correct value of mu, and the correct value of mu then makes the left-hand side equal the right-hand side. That value will have to depend on one of the parameters in the Fermi-Dirac distribution. In particular, it will have to depend on the temperature. So the energy levels are solved. They're given from Schrodinger's equation. So I know what those are. Those are just determined by the size of the box, the mass of the particles, Planck's constants, and so on. The only variable I can change is the temperature. So as I vary beta, the value of mu that I need in order to satisfy the constraint equation will change. And so then we will have to find out is that mu is then going to be a function of beta, or if you like, mu is going to be a function of temperature. And we're going to see how to calculate that shortly. Okay, so now let's look now at what Fi looks like. So the next thing we're going to do is examine the functional form of the Fermi-Dirac distribution. So the first thing we're going to do is we're going to look at it for t equals 0. Oh, I want to say something else before I do that. It's true, everything I've written is true, but I should say that mu will also depend on the number of particles. So it has to depend in this way as well, because n is the thing that's on the right-hand side. Okay. All right, so let's have a look then at what the functional form is of f as a function of energy. So let's first of all look at the case when we're at 0 temperature. So when we're at 0 temperature, so here I'm drawing epsilon, and here I'm drawing f. So imagine that that the temperature is 0. So this factor beta is 1 over basically infinity. Okay, so therefore that would be then e to the infinity will be infinity, and so f will be 0. So the value of f will depend on the sign of epsilon I minus mu. So if epsilon I is greater than mu, then we have Fi is equal to 1 over 1 plus e to the plus infinity, which is equal to 0. And if epsilon I is less than mu, then Fi is going to be 1 over 1 plus e to the minus infinity, which is equal to 1. So what we see then is that if I write mu here, then the value of f will look like this. It's going to equal 1 until I get to mu, and then it's going to drop down to be 0 after that. So in other words, the Fermi-Dirac distribution looks like a step function for t equals 0. Okay, so let's think about what does that mean. So this picture says that all states below epsilon equals mu are fully occupied. And all states above it, all states with energy greater than mu, are empty. So that's the situation at 0 temperature. So what is happening, the sort of physical picture, is that you have your n particles, your n fermions, and you start putting them into the system. So here's let me draw a sort of schematic. Here are the energy levels, whatever they are, like this. And then I get particle 1 and put it in here, particle 2, I put it in here, particle 3, I put it in here, all the way up to here's the nth particle. That's in that state here. And so then this energy level would be the energy mu. So we've just filled the particles up like that. Now, fermions can only be in the same, you can't have two fermions in the same state. If the fermions, on the other hand, have spin a half, so this is a picture for fermions, but ignoring spin. If I draw the same picture with, say, spin 1/2 fermions, which is, say, what you would have if you had electrons, for example. So now we're going to draw the same picture for fermions with spin 1/2. Well, when you have spin 1/2 for degeneracy, is 2s plus 1, and then that is equal to 2. So that means I can get two particles in any energy level. So then what I would have is particle 1 comes in, say, with spin up, particle 2 comes in with spin down, and then so on and so forth like that. And I keep going until I end up with the particles filled up, and I've got n particles now in those states like that, with two particles per energy level. So that is the picture that we have. So basically the chemical potential at T equals 0 for n particles is the energy of the highest energy level that is occupied to accommodate n fermions. And in the case of spin 1/2, which is the one that we will usually be interested in, then we can say that n is equal to 2 times the sum over energies. Epsilon is less than the chemical potential at T is equal to 0, and I just sum up to 1. So I just sum that. So that's what n is, and I want to evaluate that. So we're going to be summing over states with energies less than or equal to mu at T equals 0. And so we're going to turn the sum over states into an integral. So this is a sum over states. And so the way I'm going to think about this is the following. We know that the energy levels are for free particles. Epsilon is h bar squared k squared over 2m, because they're ideal, so there's no potential or interaction energy. And for the sum over states, we are just going to be counting the states. Summing over states means counting the states within a volume of K space. So let's figure out what that volume of K space looks like. So I draw K space in the following way. So this is K, the X component of wave number. This is the Y component. This is the Z component. I know that the energy depends on K squared. So it's an isotropic thing. So basically what's going to happen then is that this picture of occupied states is going to be a sphere in K space, an occupied sphere of states in K space, and that sphere is going to have a particular radius. So that radius is going to be what I'll call KF, like so. And then what we can say then is that the chemical potential of the highest occupied state is then h bar squared kf squared over 2m. We don't yet know what kf is, so we need to, you will find this. So our picture is we have states that are occupied outside the sphere, then they're not occupied. So then we can calculate what kf is. So we can say then that n is equal to 2, that the 2 comes from spin degeneracy. So n is equal to 2 times the sum over states labeled by k, and now the value of k has to be a number that is less than or equal to this value kf, and so that is equal to 2 times the density of states in K space, which is V over 8 pi cubed, and then the integral from 0 to Kf times the integral over the volume of K space. We're integrating over the volume of the sphere, so this is going to be 2 times V over 8 pi cubed times 4/3 pi kf cubed, because that's the volume of a sphere in 3 dimensions. And so then that means that kf is equal to 3 pi squared n over v to the 1/3 power. So what I've done is I've said we're going to occupy all these states. I'm throwing my particles into all these states. These states are a sphere in K space. We don't know what the radius of that sphere is, but we know that if I work out the volume, the volume of that sphere, that has to then be proportional to the number of particles that I'm putting in. And then I've just done the simple calculation, integrating over K space, to find that the radius of that sphere has to go like the number density of the particles times 3 pi squared raised to the power 1/3. And once I know Kf, then I know what the chemical potential is at zero temperature and N, and that is then equal to h bar squared over 2m, and then k squared, which is kf squared. So that's then 3 pi squared n over v raised to the power 2/3. So that is the chemical potential at zero temperature. And this has a name. So this is called, we write this in solid state physics at least, this is known, or actually any area of physics, this is known as the Fermi energy. And this Kf is known as the Fermi wave vector. And now we can then work out what the epsilon f is. We can associate. So this Fermi energy, by the way, this is just purely kinetic energy, right? Because this is just the kinetic energy of the particles the floating around using the non-relativistic formula for the energy as a function of momentum. And we can I'll come back to you in a second. And then we can define a Fermi temperature. And we define that by saying, let's write down this Fermi energy as Kb times some temperature, and that gives us the Fermi temperature. And lastly, there's a Fermi velocity, which is how fast particles are moving with the Fermi energy. So that's just saying the energy is a half mv squared. So therefore, that Fermi velocity is equal to 2 epsilon f over m to the 1/2. Okay, Gabriel. No, you're not Gabriel. Okay, Luke. No, Charles. No, Arvind. Okay, you're in the wrong place.
Yes.
Okay, what's your question?
So so in this case, we had I guess we had like a really sharp transition from like occupied state 1 to 0 because
Yes.
it's at 0 temperature.
Yes,
So if we're at non-zero temperature, we
I'm going to come to that.
yeah, it would be like smooth.
I'm going to show it to you in a minute, yes.
Okay, so but is there still like a concept of like a Fermi energy in that non-zero temperature case where it's not a sharp transition?
I mean, not, I mean, you can say that, you can always say, here's the Fermi energy. The Fermi energy is just what the chemical potential would be at zero temperature. So that'll just be in the middle of this transition zone.
I see.
Okay?
Okay.
And I'm going to draw that in like just a minute. Did I answer your question?
I think so, yeah.
Yep. You think so? You're not sure?
No, it does. It does.
Okay. Okay. All right. So that's all things Fermi. And where do we apply this to? So we usually apply this to electrons in a metal. And in that particular case, the Fermi temperature is typically about 10 to the 4 Kelvin. And that's because N over V might be, I don't know, 10 to the 22 per cubic centimeter. So you get something like 10 to the 4. And then usually then T over TF is usually much less than 1. So that means that the Fermi-Dirac distribution is slightly broader than a step function. And so let's go and work out, we're going to now talk about what that is. So let's draw a picture then of what Arvind was just asking about. So here is our picture. So here is our Fermi-Dirac distribution. Here is 1 and 0. So somewhere here is our Fermi energy, and I'll draw in blue the 0 temperature behavior. So that's what happens at T equals 0. And now if I'm at a somewhat higher temperature, then what this is going to look like is something like this. So it's a kind of, there's not a very good drawing of it actually, but it's something like that. So so we're going to investigate the properties of that. Jake has a question.
And what is the Fermi temperature?
It doesn't, it just tells, it's just in temperature. And then if you look at the, what your real temperature is, the temperature of your system you're looking at, if it's much less than 1, as it normally is, then the distribution will look like this. So this picture here is T much less than TF, but greater than 0. And what do you think it would look like if T was much higher than TF? Well, so then if T was much higher than TF, then what would happen? Well, we already know the answer because I've told it to you before. Now what's going to happen is all these states out here would be occupied. And so you'd have something that looks like this. So this would be T much greater than TF. So then what's happening is most of the states have got a very small occupation number. And so this would be the classical limit. And then this limit, which I'm drawing you over here, this limit would be the quantum degeneracy limit. And it's called degeneracy because we've got pretty much for most of the states, 2 particles per state, spin up and spin down. Then there's a transition zone where they vary. And then beyond the Fermi surface, then there is no states at all. Oh, I didn't use this term. I want to use this term. I said the words Fermi surface. So we think of this thing, this object in K space, has a name. Let's call the Fermi surface. Okay. All right. So I answered your question, Jake. So it just tells you. So knowing the Fermi temperature enables you to say whether I'm in the quantum degeneracy limit or I'm in the classical limit, where in the classical limit the average occupation of states is very much smaller than 1, as we've talked about before. Okay, Andrew.
So,
Andrew and then Chia. Yeah.
So, in the case of T is equal to 0.
In the case of what?
In the case of T is equal to 0.
Yes.
The Fermi energy and potential are the same, but at higher temperatures, does the chemical potential shift?
At higher temperatures, the chemical potential shifts, and we're going to talk about that. But the Fermi energy is defined as the chemical potential at 0 temperature. Okay, Chia, you had a question?
Yeah, I'm just confused because my understanding is K is really discrete. Is it?
Yes, K is discrete, and then as we've talked about before, now so K goes as 2 pi over L times a set of integers, nx, ny, and z. And then as we take L goes to infinity, so we make the system size bigger and bigger, then the spacing between the energy levels, the spacing between the K values gets smaller and smaller. And so we can replace the sum over quantum numbers by an integral. Okay, and then we did the integral over K space, and that's how I got the result. That's how I got the thing over here on the left. Did I answer your question?
Yeah.
Sure?
Yes.
Okay. All right. So let's just ask one last question before we calculate the excited states. So by the way, so the energy in the ground state sorry, energy in T equals 0 is U is equal to the sum over I, Fi times epsilon I. So that's the expected value of the energy, the sum over the single particle quantum states, the energy of those single particle quantum states times their average occupation number. And let's go ahead and calculate that. So U, the average energy, is then equal to 2 for spin degeneracy, then our factor of density of states in K space, V over 2 pi cubed, the integral up to the Fermi wave number, Kf, excuse me, then 4 pi K squared dk. That's just writing d3k. And then the thing that's my integrand, the thing that's inside the integral is h bar squared k squared over 2m. So this part over here is the d3k written in spherical polars. This thing here is the energy. And then if I do that integral, then what I get is 3/5 times n, the number of particles, times the Fermi energy. And that's something that I recommend that you check so that you know where that comes from. Okay, so now let's ask what is the energy when we're slightly above 0 temperature. So what we're going to do is I'm going to calculate this, and first we're going to calculate approximately by ignoring the change in mu. So we're going to assume for this calculation that mu of t is roughly equal to mu of 0. Okay, and the reason that we can do that is for simplicity. And so what we're basically saying is that mu of t is equal to mu of 0, which is the Fermi energy, plus t d mu by dt at t equals 0 plus higher order terms, and this is close to the Fermi energy. So there will be a correction that comes from the d mu by dt term, but for simplicity, I'm not going to calculate it for now. Okay, so why is this why is this a good approximation? Well, because if I look at the shape of this curve, so here is f, here is epsilon, here is 1 and 0. So here is what I have at 0 temperature. So that's my 0 temperature curve. Now, when I've excited the system, then we're going to make the approximation that the number of particles that are depleted from here is the number that have been added here. So by ignoring the shift in the chemical potential, which you can take into account, and it makes a higher order correction to what we're going to compute, then what's going to happen is we can just simply say that what has happened is that particles that had energy here have now moved to having energy above the Fermi energy. So then we can calculate what the energy is at very low temperatures. So it's going to be U of 0. So this is an approximate calculation. And then it's plus. And now what is it plus? Well, what I've done is I've shifted the energy of shifting fermions from energy epsilon F minus some epsilon prime to epsilon F plus epsilon prime. So I'm saying that this shift here, that's the thing that I'm calling epsilon prime. So that's the thing. So the energy gain, if I take a particle that's at energy epsilon prime below the Fermi surface and move it to an energy epsilon prime above the Fermi surface, then what I've done is I've added 2 epsilon prime to the energy of the system. So then what I'm going to have to do is I'm going to integrate from naught to infinity d epsilon prime to epsilon prime, because that's I've gone from minus epsilon prime to plus epsilon prime, so that's 2. And then I have the Fermi-Dirac distribution evaluated at epsilon prime, and then I have the density of states and energy evaluated at the Fermi surface. So this is the density of states in energy. That's the Fermi surface at epsilon prime. F prime is the Fermi-Dirac distribution, and this is the shifting energy. So then you would have to do that integral. So you do the integral, and what you get is that u of t is equal to u of 0 plus the density of states. I'll write it down for you in a minute. It turns out to be this, and then we have a number which is pi squared over 12, and then 2 times kb t squared. And how did I do this integral? How did I do this? So here's what I did. First of all, the density of states in energy, we've worked that out before. And so that is V over 2 pi squared times 2m over h bar squared over to the 3 halves times epsilon f to the 1/2. So that's what it is, using the fact that we have spin 1/2 fermions as we do in a metal. So that's the density of states formula in energy that I wrote down for you a couple of weeks ago. And then we know what the Fermi energy is. So then, because that's 3 pi squared times n over v times to the power 2/3. So this ends up being 3n over 2 times the Fermi energy. So you should check this. And how did I do the integral? So the integral is then done like this. So I use the fact, so if I have this integral to do, so the integral so d of epsilon f is just a number, so that comes out of the integral. So the f is the Fermi-Dirac distribution. So the actual integral I have to do is epsilon prime d epsilon prime times 1 over 1 plus e to the epsilon prime over kbt. So that is the integral that I have to do. That's the hard calculation I have to do. Where does the chemical potential go? The Fermi-Dirac distribution has a chemical potential. Where does it go? Why isn't it in this integral? Say it again.
We said it was EF.
So, sort of, yeah. What are you going to say, Jake?
We said for low temperatures it was different energy,
Yes, but why isn't it in the integral?
because then you take out from the.
I didn't really take it out. Okay, what I did was I measured the energy with respect to the Fermi surface, right? So the thing that would be in the integral is epsilon minus mu, which is epsilon minus epsilon f, and then my epsilon prime is defined as epsilon minus mu, right? The energy over here is defined, epsilon prime is defined as the distance from the Fermi surface. So that's why epsilon minus mu, the mu's already gone out. So this is the integral I have to do. And like all integrals of this sort that you have to do, the trick is a change variable. So that so a new variable x is epsilon prime over kbt. And so then you can immediately see where this factor of kbt squared came from. Okay, so why this factor of kbt squared? So if I do that, then dx is equal to d epsilon prime, and then I have kbt coming in there. So then this integral then becomes the integral from 0 to infinity. Epsilon is x times kbt. D epsilon is dx times kbt. And then I have 1 over 1 plus e to the x. Okay, and so then I get kbt squared times the integral from 0 to infinity dx over 1 plus e to the x. And you can do that integral, and that integral is kbt squared times pi squared over 12, something like that. And you can do that integral by doing contour integration and complex variables. Yes, Arvind.
So if the integration variable epsilon prime is now the difference between I guess the point and the Fermi energy, why is the integration bounds from 0 to infinity instead of like negative?
Because I've assumed that this shape is symmetric about the Fermi surface, and so then I put in a factor of 2 in order to go from one side to the other. Okay, so you should go and check that.
But then
So it's not what. Okay.
But like the absolute energy can't be like less than 0, right? So we can't like why can we do this with the upper bound to infinity? Shouldn't like we can only do the upper bound to like EF and then have like the remainder from like
the distance the distance from the Fermi energy can go all the way up to infinity.
On the right hand side, but not on the left.
Right, but remember that we are at temperatures much smaller than the Fermi temperature. So basically the size of this region, this transition region, this width of this transition region, the width of that is of order kBT, right? Because that's thermal energy that is exciting things. And T is much less than TF. So this energy, this here, this is kBTF, and that's much greater than that. So the error I'm making by extending the integral all the way to infinity on the left-hand side is exponentially small. Do you understand? Okay. So right. So that's the internal energy. And then if I look at the heat capacity, so that then is the heat capacity is du by dt. And so that is going to equal then pi squared over 2 n times kb times t over tf. So that's the heat capacity. And so there's two things to notice about this. So comment number one is that C is proportional to T at low temperature. And this is a quantum effect. Why is it a quantum effect? Well, suppose I looked at the heat capacity for a classical system. Well, for the classical system, U is 3/2 N kBT. We already calculated that. So that means that the heat capacity for a classical system is going to equal 3/2 N kB, and that's equal to a constant and doesn't have any temperature dependence. So what that means is that the heat capacity for, and this is heat capacity is a constant volume, by the way, the heat capacity for the Fermi-Dirac fermions is much, much less than the heat capacity for classical particles. And this is a quantum effect. And why is it a quantum effect? It's a quantum effect because only the particles that are near the Fermi surface can be thermally excited. And T is much less than TF. And so it's a thin shell. And so basically, the Pauli exclusion principle means that particles in quantum states with energy much, much less than the Fermi energy cannot be excited into higher states. And so that's sometimes called Pauli blocking. And so the heat capacity of electrons in a metal goes linearly with temperature. And this is one of the first great successes of quantum statistical mechanics, was being able to explain this fact. Now, what we've done here is note that we ignored, so comment number 2, we ignored the fact that mu is equal to a function of temperature. So what would it look like as a function of temperature? So let's write it down in the continuum. So now let's write down the continuum equation. So the constraint equation. So the constraint equation is formally this, and now let's run it into the continuum. So then this turns out to be V over 2 pi squared, the integral from 0 to infinity, 2m over h bar squared to the 3/2. That's the density of states and energy. And then epsilon to the 1/2 d epsilon, and then our Fermi factor, which is e to the epsilon minus mu, now as a function of temperature, divided by kBT plus 1. And so here's the thing, you can see that this number here is fixed. That's just the average number of particles in the system, which is very, very sharply peaked around, say, 10 to the 23 or whatever it happens to be. And then everything else in this integral is a constant The only thing that varies is there's a factor of temperature. And because there's a factor of temperature there, then that means that mu itself must be a function of temperature. So that the left-hand side is equal to the right-hand side. Why do we need that? Well, this is fixed and therefore is not a function of temperature. Well, certainly not a strong function of temperature. I want to be precise. And so then what we can do is then solve this equation in some way, let's say numerically, in order to find out what mu is as a function of temperature. So let's have a look at that, what that looks like. So here I'm drawing temperature, and I'm going to normalize it by the Fermi temperature. Here I'm going to draw the chemical potential, and I'm going to non-dimensionalize it by dividing by the value at t equals 0. So here is 0, and then this value over here is equal to 1. And then this value here is 1, this is 2, and so on. And then the actual curve looks something like this. It's kind of a bit compressed the way I've drawn it. Something like that. So it starts off positive at 1 at 0 temperature, and then goes down. And so as we go to high temperatures, T much greater than TF, then that means that mu is negative, and its magnitude is much greater than the Fermi energy, and therefore what happens is that the Fermi-Dirac distribution then looks like E to the mu over kBt times E to the minus epsilon of kBt, and this then is sort of roughly like a Boltzmann distribution. But remember, the Boltzmann distribution is for the many-body quantum state, and this here is just the single particle quantum state. And what this then applies, for this to apply, we need that kBt is much, much larger than epsilon f. And if you look at what this condition implies, that means that the thermal de Broglie wavelength is much greater than n over v to the 1/3. And this condition is what we derived on general grounds last lecture. If we're in the classical limit, then that's what has to happen. Okay, so now let's talk about what happens to the equation of state. So the thing that we really would like to know is the equation of state. And when I talk about the equation of state for gas, what I mean is PV is nkBT. That's the equation of state for an ideal classical gas. Now I want to know what the equation of state is for a quantum gas. And for doing that, I want to now calculate it properly. And I want to compute the grand partition function directly without using my physical intuition of the dirty trick. So what we're going to do is now we're going to calculate this. We're going to calculate this systematically. And no dirty tricks. Okay, so So this is the bit that if you've fallen asleep up to now, this is when you really want to wake up. Okay, so let's write down the formal statement for the grand partition function. So our formal statement for the grand partition function is the thing that we wrote down last time. Let me just remind you what it is. So first of all, we sum over the total number of particles in our system. And in the grand partition function, we sum from n equals 0 to infinity. So we allow there to be a non-constant number of particles in the system. Then what we do is then we have to do the sum over the occupation numbers of the different quantum states. So now we sum over, no, that's really bad. I didn't want to do that. So let's try again. Okay, so now we sum over the occupation numbers of the particles. So we're going to sum n1, I'm going to sum over n2, and so on and so forth. So we're summing over now the occupation numbers of every quantum state. And in the case of fermions, these sums go from 0 to 1, 0 to 1. In the case of bosons, they'll go from 0 to infinity. And then we have our Gibbs distribution. So now Gibbs distribution is e to the minus beta times the energy. The energy of the system is I sum over the states, Ni, the occupation number of the states, times the, whoops, not I, J. So J is a dummy variable. I sum over the occupation number of the state J, the energy of state J, and then I have to put in the chemical potential, which is then a term that looks like e to the minus beta mu. So that is beta mu times then the occupation number, let's call it J, a dummy variable of Nj. So that is the grand partition function. And then the hard part about this is that all of this has to be under the constraint that if I add up the occupation number of the states, Nj, then that has to equal the total number of particles in the system. So first of all, in the outer sum, you tell me how many particles there are. 0, 1, 2, 3, all the way up to infinity. Then given that number n, then I sum over the occupation numbers of the quantum states, my Gibbs factor, e to the minus beta energy minus mu over kT. And then for these states here, given that I've told you what n is, what the capital N is, inside this sum, I already know what n is, and that has to be summed up has to sum to equal n. So that, as we explained last time, is the thing that is particularly difficult to do. So now let's write this out in a way using delta functions, just for completeness. So another way I can write this is the sum from n is equal to 0 to n is equal to infinity, and then once I've chosen how many particles there are in the system, then I sum over all the occupation numbers being from 0 to 1. And then these exponentials on the left-hand side, these ones here, these are e to the sum of something. So e to the sum of something is then the product of each of the things, right? Okay, so those are just products. So then I can write that as the product from over all the states, J, and then e to the beta mu minus epsilon j times nj, like so. So that's the sum. And then I could write down the constraint as simply a Kronecker delta. So I write this down, delta of k, so it's a Kronecker delta of n minus the sum over the occupation numbers, nj. So that's what this thing formally is, and then I close the outside bracket, and that is what the grand partition function is. Okay, so now let's think about what this looks like. So we've got inside here some nasty function. So let's call this function, let's have a look, let's call this function some function that depends on the occupation numbers. Okay, so I want to now think about this. So now we consider the sum over n, 0 to infinity, and then let's write out so it's the sum from n equals 0 to infinity. Then I have the sum over the occupation numbers. Then I have the function that I'm trying to sum over, which in our case is given by the Gibbs distribution. And then I have my delta function that says that the sum of those occupation numbers has to equal the n that is on the outside. Okay, so that's the thing that we're trying to solve. So let's write out all the terms in this, and we're going to write out the terms for capital N equals 0, 1, 2, 3, and so on. So this is equal to the following. First of all, it's the sum over the occupation numbers of this function, whatever it is, but subject to the constraint that the sum over I of ni is equal to 0. That's the first term. Then the next term is the same thing, sum over the occupation numbers, the thing that I'm trying to sum over, like that. But in this case, now the sum over the occupation numbers has to always add up to 1. Then the next term is the same thing, summing over the occupation numbers of my function, f of ni, but now with the sum over ni is equal to 2. And then plus, and then dot, 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 all the way up to the sum from the occupation numbers, f over ni, and now in this case, the sum over the ni's is equal to infinity. So that's what this whole thing is equal to. Okay, so I've just said, let's take in case n equals 0, write up this. In case n equals 1, write up this. In case n equals 2, write up this term all the way up like this. And so now you can see that this is the sum of this function, but there's no constraint, because the value of this sum can be when the sum of the ends, the value of this constraint is when the sum of the ends can be 0 or 1 or 2 or 3 or anything I want. And so this then is then equal to the sum over all the ni's of f of ni. And that sum can go up, the sum of the ni's can be 0 or 1 or 2 or any number you like. So in fact, it's an unconstrained sum. So now the constraint has gone away. So I never have to worry about it. So if I want to do the grand partition function and I have to worry about this nasty constraint, goes away. And that's the magic of the grand partition function. Because now I can do the thing in a very simple way. So now, I know you got your hand up, Jake, I'll come to you in a second. So now let's go back to the grand partition function. So, okay, so what does this mean for StatMech? So what it means then is that when I write down the grand partition function, I don't have to worry about the constraint. I can literally, on the left-hand side here, just literally cross this out and cross this out, and I just have the sums over the occupation numbers, which is a product, times the product of the Gibbs factors. So this then is just equal to the sum over the Ni, which means sum over N1, sum over N2, sum over N3 multiplied together, times the product over the states of e to the beta mu minus epsilon I times Ni. And this thing here, just to make sure everybody's on the same page, this just means sum over N1, sum over N2, etc. It's a product of summations. And so now that means that the grand partition function factorizes. And so therefore, so chi is equal to then the product over states of the sum over Ni is equal to 0 to 1, e to the beta mu minus epsilon I Ni. And this then, inside there, I've got two terms. Ni can be 0 or 1. So this then is the product over states of 1 plus e to the minus beta epsilon I minus mu. And then the equation of state well, remember what the equation of state is for the grand partition function. I proved that to you last week, that PV over KBT, which is what I call the grand potential, is then just equal to logarithm of chi, and so therefore it's the sum of the quantum states of the logarithm of 1 plus e to the minus beta epsilon I minus mu. So that is the equation of state. It just drops out because the grand partition function factorizes. That's the whole reason why we do the grand canonical distribution. This equation of state, where did this came from? This came from the fact that the grand potential, which I called phi, is equal to minus PV, and that was minus KBT times the logarithm of chi. So when we introduced the Gibbs free energy, that's how I derived that for you. So you could go back and check that. And so this is, all I've got to do now is sum over states. That sum over states gets turned into an integral. I'll write that down for you in just a minute. So this is the equation of state. It just drops out of this magic of the grand partition function. And then the question you have to ask is, but wait a minute, what is the chemical potential? Okay. So there's a mu in there. What is the value of mu? Well, remember that n is written down. N is the sum over Fi. That's the constraint equation. And I also showed you before that that is equal to lambda times d by d lambda of the logarithm of the grand partition function, where lambda was the fugacity, which is just e to the beta mu. So that equation, this equation over here, determines this equation determines mu, and once I know mu, I can plug it into the equation of state and solve the two things together. So what that means is that in any grand partition function, has two simultaneous equations. Now I wrote them down for you here in terms of this abstract notion of just summing over states. So let me make it more precise. So let's write the sum over I into integrals over k. So let's just end by writing down what those formulae are. So then what I'll get is that PV over KBT is equal to V over 2 pi cubed times the integral d3k of the logarithm of 1 plus lambda e to the minus beta h bar squared k squared over 2m. So that's the equation of PV over KT. And here there's no spin degeneracy. And then the constraint equation then is n over v is then the integral of the same thing, v over 2 pi cubed integral d3k of 1 over 1 plus lambda to the minus 1 e to the h bar squared k squared over 2m. So this equation over here, this determines lambda, and then that lambda comes in over here, and so that's the full solution for how I determine the statistical mechanics of quantum particles. Okay, so that's the end. I'm going to just write this down in terms of two functions, and then I'll finish. So conventional to write like this. So I'm going to say that P over KBT is equal to this. So 4 pi over h cubed 1 plus 2 times the spin degeneracy, the integral from 0 to infinity of p squared dp. So I'm going to write p is equal to h bar k, p squared dp times the logarithm of 1 plus lambda e to the minus beta p squared over 2m. So that's the first integral. And then n over v is equal to 4 pi over h cubed, spin degeneracy 1 plus 2s times the integral from naught to infinity, p squared dp over 1 plus lambda to the minus 1 e to the beta p squared over 2n. And those two things solved together give you the solution. All right, so I'm going to stop there. So we can, the next thing I'm going to do is when next time we lecture is I'm going to look at the properties of these integrals. And what we're going to see in particular is that in the classical limit, we just get that PV over NK BT is equal to 1. And then I'm going to look at the leading quantum correction to this. In other words, what is the equation of state now when we have quantum corrections, lowest order quantum corrections added to the classical result? Okay, so I'm going to stop there. Questions? Did you have a question, Jake?
Yes, could you explain again? Could you go back?
What do you want me to do?
I'm confused about why the constraint, why it's unconstrained after you write out all those terms.
Well, write out all the terms, okay? Is there any constraint on which terms are allowed to be there? The sums over the f, the sums over the n's can be any number you like. So they're not constrained. Whereas if I look at the thing on the left-hand side, now, look over here. I look at the left-hand side, inside these square brackets, there's a constraint,
Yes.
right? And some of it in this sum has to equal n. And when I sum it at n, then there's no constraint left at all. There's just no unconstrained sum. And an unconstrained sum is a product of terms. So every term is represented there, so there's no constraints left. So that's the magic of summing over n. So write out, so after this, write out all those terms and just see there's no constraints. Okay? Okay, Andrew.
So why exactly do you have the sum and the exponents in the exponent?
Why do I have the sums and the exponents?
Yeah.
Do you mean
You're summing over the n sub, you're summing over j, now it was j.
J is a dummy variable? This one here? This one
Yeah,
here? Yeah, this one. Right. So J is summing over states. And I'm summing over all states, so this is a dummy variable. So you tell me, so J goes from, so this is summing over all states, then J's go to zero. But this is what the energy is, the occupation of the state, then the energy of the state.
Oh, so, yeah, then for each j, you sum from 0 to 1.
Yeah.
That's fine.
I sum from 0 to 1 because that's what this sum here.
Exactly.
Okay. Any other questions? I know this is a lot to process. Okay, I strongly advise you to just go through this afterwards, after today's lecture, and just understand if there's one thing I want you to take away from this, is that the sum in the grand canonical distribution, the sum is unconstrained, and because of that, what it means is that the grand partition function factorizes. And because the grand partition factorizes, then I can write down the equations that are on the top of the right-hand page. And that's the thing that means I can do it exactly. No constraints, none of the stuff that would if I was doing the canonical distribution, I would have to say n is fixed. And if n is fixed, then all those sums have to be constrained to sum up, the occupation numbers have to sum up to n. When the grand canonical distribution, There's no constraint, and so the thing factorizes. The canonical distribution is hard because the constraints are there, and so it doesn't factorize. But the grand canonical distribution, it factorizes, and so that's how I can write down these lovely equations here, where it's just a very simple product of things, and then I take the logarithm, and then it becomes just a sum of terms. So that's the magical effect of having the grand canonical distribution. Okay, that's the thing that nobody ever told you before. How many people knew that before? Okay, nobody. Okay. This is the thing that's not in any book except my book. Okay, so, but this is why it works, and this is why you can do it. Okay, so now you know physically what the grand canonical distribution means. It means that little cartoon picture that I'm always drawing, wherever it is, somewhere here. Yeah, the picture on the left-hand panel. That's the thing that it means. It's just that picture on the left. So it's a natural, intuitive thing. And then mathematically, the reason that it's great is that the grand partition function factorizes. So it's more natural and it makes the calculation easier. What more could you ask for? Okay.